Anyway, so now let's say that we have a bunch of vectors that are now orthonormal. By the way, I'm going to try and put hats over vectors that are unit length and orthogonal to one another. And we want to first, if we want to project onto a unit length, just a single unit length vector, right? Well, here's our formula, right? But what is a dot a if this thing is unit length? Well, this is just the norm of a squared. Okay, so this goes away, and you get this nice formula for the projection. You know? What if you want to project onto more than one? Well, let's do that. So, right. I gotta write smaller, so I have to keep doing it. Okay. So what do we do now? Well, now we have a bunch of unknowns, right? C1 all the way to CK, which is going to be the projection of B onto the span of these guys. Right? So let's write this down. So we have C1 A1 plus CK AK, right? And this sum here is going to be the projection that you want. Right? But the C's are unknown. Minus this vector B. And we'll square it, because that's what makes all of our math easy. Right? And now we're going to do our big FOIL on this thing. Right? This is the dot product with itself. So once again, we get this double sum. Right? So first, we'll get a bunch of dot products between pairwise terms in this sum. Right? So you'll get a sum over ij, ci, cj, a I hat dot a j hat. Right? And you'll get a bunch of dot products between these guys and these guys. Right? This is minus sum over I of 2 times B dot AI and CI. Right? And then finally, you get the dot product of this guy with itself, which is just the norm of B squared. Everybody see what I did here? All I did was just treat this like a product with itself and expand out that product as far as I could. Now, what do we know about this first sum here? Well, we see that we've got a bunch of dot products between different A's, right? And we know, we have an expression for what this dot product is because these guys are all orthogonal, orthonormal in fact, right? In particular, any term for which I is not equal to j vanishes, and any term for which I is equal to j does what? It gives you 1. Right? So let's simplify it just a little bit. Ugh, I hate this board. So this is the sum ci squared, right? And then we're going to go ahead and just group that with this additional term, right? Minus 2ci ai hat dot b plus mod b squared. Okay? And we want to minimize this thing with respect to all of the different c's. So let's take his, we'll call him E, again, I guess E twiddle for fun. And we have to take his derivative with respect to each of the c's and set it equal to 0, right? The usual story for minimization. Let's do that. dE twiddle dci. Well, okay, so first of all, this guy isn't a function of c. Okay? And what happens here? Well, each sum only involves one of the c's, right? So only one term survives, and we get 2ci minus 2ai hat dot b. Yeah? And in particular, this shows us that ci is equal to ai hat dot b, which is what we sort of expected, right? Remember, we already showed that the projection onto a single unit thing is this guy. All we prove now is that the projection onto the span of a bunch of orthonormal vectors is just a bunch of summed up things that look like the same projection. But that is something you have to check, right? It's not something that we know ahead of time. In fact, by the way, this proof shows up in Fourier analysis a lot, right? It's basically the same pattern. But anyway, this is what we got when we worked through our math, took our derivatives, did all the usual things for minimization. In particular, this tells you that the projection of B onto the span of all of these orthonormal vectors, it has this very nice form. Right? Is this true if the AIs are not orthonormal? Absolutely not, right? This step here becomes invalid. And you have some yuckier formula, right? A change of basis or something, but we're not going to worry about that. Okay, so this suggests that there's actually a pretty simple algorithm for orthogonalizing a set of vectors. Does everybody know what I mean when I say orthogonalizing, by the way? No, you guys are so quiet today. So the basic idea here is I have a bunch of vectors v, right? And if I orthogonalize them, I want to come up with a new set of vectors, which I think I call A hats. And the span of that vectors will be the same as the span of the v's, but they'll be orthonormal. Right? And there's sort of an obvious way to do this, which is what Gramschmidt is really encoding. Right? So the first step of Gramschmidt says we're just going to take the first vector v1 and leave him alone, but he's got to be unit length, so we'll divide it by his norm. Yeah? By the way, I'm going to assume that these vectors are non-zero. We'll just throw them out if they are zero. Right? I didn't write that analogy. Okay, so A1 will just be v1. So what is the span of our starting set of A's? Well, it's just v, the same as the span of v. Yeah? Because this thing is parallel to v. Now we have to do our iterative thing. So now we're going to look at, say, v2, and we're going to project him onto v1. Yeah? Which of course is easy now that we have this formula, and we're going to assume inductively that our A's are orthonormal. So we'll project out the component that's parallel to the guys that we already have, right? And then we'll just say our next A is equal to that thing, you know, the difference between the V that we started with and its projection divided by its norm, right? We have to divide by its norm because it has to be unit length, right? And we know at every step that this A is orthogonal to all the A's that came before it just by properties of the projection that we already showed. This is a lot of words. Are you guys following? Hands if you're following? If you're not, you should be asking questions. Okay. Right? So again, what does our algorithm look like? Well, let's just go through one iteration really quick. So let's say, unfortunately, boards are flat, so you really can't do more than one iteration with any of these things. But let's say that this is V2 and this is V1. Right? So what are we going to do? Well, first we're going to say, okay, we're going to normalize him, and we'll make A1 is just some unit length vector that's parallel to V1. Right? And then what are we going to do? Well, we will project V2 onto A1. We'll call him P2, I think. Right? Oh, these should all, this class I'm trying to be careful with. Use this stuff. So here's the projection, and then what is going to be A2? Well, I'm going to subtract off the projection, which gives you this thing which is perpendicular to the first vector I started with, and then I'm just going to normalize it to unit length. Right, so this algorithm is actually pretty straightforward, right? Every time you get a new vector, you project it onto the guys you've already seen, you remove the projection, and then you normalize. Yeah? And I think this is covered in linear algebra classes, because theoretically, this is the beginning and ending of the orthogonalization story. Right? You now have a method that is guaranteed to work for orthogonalizing vectors. Yeah? But it's not the end of the story for us. Yes?
So this depends on how you name V1 to retake. Like if you reorder.
Yes. If you reorder your vectors, you will get a different set of orthogonal things. Very important property. In fact, this is true for QR also. If you reorder your columns of A, you may get a different factorization, which is going to be abundantly clear in a second. All right, and how do you prove that Gramschmidt works? Well, it's quite simple. You can prove a pretty easy inductive statement, which is that for each I, so sort of in each step of your algorithm, the span of the things that you're computing and the span of the vectors you considered so far is the same. Right? And this is sort of an obvious claim, right? It's certainly true for one vector, because all you did was divide by its norm. And then inductively you say, well, all I'm doing is projecting out the span of the stuff I've already seen, so I haven't removed any information that I didn't already know. Okay, so great, so we know how to orthogonalize, and in fact, we can implement Gramschmidt using column operations, right? Because what am I doing effectively? Like if I took all of those V's and I stuck them in the columns of a matrix A, right? Then all of the operations of Gramschmidt involve taking some column, right? Scaling it by something and subtracting it by from another column, right? That's this projection operation. Or normalizing a column, which is just equal to post-multiplication by a diagonal thing, yeah? And in fact, this thing where you're subtracting out the projection, what do you know? Well, if I'm doing QR and I have a matrix that looks like this, right? If I'm implementing Gramschmidt, then at some step in my Gramschmidt algorithm, I'll say, okay, these things are orthonormal, but these ones I don't know anything about yet because I just haven't processed them. Right? So what am I going to do in each step of Gramschmidt? Well, I'm going to subtract off multiples of the guys to his left. Right? left, in fact, correct? So, in the end, what are all of the matrices that I'm post-multiplying by going to look like? They're all going to be upper triangular, because they involve interactions of this column with things with indices smaller than it. Yeah? So if I implement QR by a bunch of, a bunch of post-multiplies by these little elimination matrices, which again, we would never do in practice, but theoretically is useful. Right? I can't emphasize that enough. Then what happens is eventually we're going to get something orthonormal, right? When Gramschmidt is done, the columns of A are just orthogonal and unit length, right, by definition. And it's going to look like A times E1 times E2 times EK. Right? These things are all upper triangular. Right? And you proved on your homework that's due today that the product of upper triangular things is upper triangular. And you prove the inverse of an upper triangular thing is upper triangular. So if we call this thing R negative 1, right, we'll just assume he has an inverse because he does. Then we know that A is equal to QR and that this thing is upper triangular and this is orthogonal. So we've proved that such an object exists by Gramschmidt. Yeah? So, our story is sort of done and sort of not done. We have a technique for computing QR factorization. It runs in okay time, right? It's still n squared looking, or I guess n cubed if you count the projection step. Right? So it runs in the same amount of time as Gaussian elimination or anything else. But numerically, this thing sucks. Let's think about why. Oh, oops. Yeah, so here it is, in big font. This is our new pattern. Anytime there's something I want you to learn, it's in big font. Or small font, you should learn it all. Okay. So, also on your homework, on these problems that everybody's complaining to me about, sorry, is this idea of catastrophic cancellation. And what happens here is that oftentimes when you subtract two big numbers, you can end up with a small number, but a number that's non-zero. Right? So like, for example, if I have like 1 plus epsilon and I have 1, right, and I subtract these, I get epsilon, right? But then I don't want to divide by that number, even if these two things are big. So subtraction is one of these operations to be very careful about. Or addition by negative numbers. By the way, again, on your homework, negative numbers exist. Please. If I get one more question about this. Okay, so anyway, let's say that we have two vectors, v1 equals 1, 1, and v2 equals 1 plus epsilon 1. Can anybody give me an orthogonal basis for the span of these two guys? I'm going to grab my notes because I'm going to keep this calculation wrong. Come on, there are two vectors. They're clearly linearly independent. So what is a basis for their span?
1, 0, 0, 1.
Yeah, the identity basis, right? Because there are two of them and they span R2. Yeah? That's all you need. So in fact, numerically, sort of, this isn't a hard problem. But what happens when I run Gramschmidt? Well, let's just do it because it's only 2 iterations. So first, the first iteration, right, all I have to do is we say, is this guy divided by his norm? Right, so this is 1 over the square root of 2. Yeah? Now what is the projection of V2 onto V1, or equivalently onto A1? Well, you take the dot product with this guy, right, and you divide by the norm and so on, you do all these fun and games. But if you believe me, it looks like this. Right, just by applying this formula we have. So in the end, right, what is the vector that we're going to want to normalize to get the second piece of our basis? Well, it looks like V2 minus the projection onto the stuff we've already computed. In this case, it's just A1, V2, right? This is sort of the remaining piece of V2 that we haven't seen yet. Right? And so what is this going to be? Well, it's 1 plus epsilon 1 minus 2 plus epsilon over 2 times 1, 1. Yeah? And this object is equal to 1/2 epsilon minus epsilon. What is the norm of this thing? Basically 0. Right? In particular, when I compute the norm, what's going to happen? Well, I'm going to square these two numbers. So if epsilon is already small, then epsilon squared is like ridiculously small. Now I'm going to add them together and I'm going to divide by this stuff. right? And so what happens is we're dividing things by ridiculously small numbers. In fact, we're dividing small numbers by even smaller numbers. And in the end, who knows what we're going to get? It's going to be total garbage because we can't divide by really small things, right? This is sort of the takeaway of the homework that's due today, right? You divide by small stuff, and all of a sudden, you can have explosion and all kinds of numerical issues. So this happens, obviously this little toy example is easily avoidable in Gramschmidt, but the problem is that if you are or if you want an orthogonal basis for say 500 vectors, right? Think about this process, right? The more iterations you do, the more times you have to subtract and project and subtract and project, and eventually your projection might be very small. That is that the first like k vectors span like 99% of the space, and now you're just dealing with the little bits of the space that are left. And this little phenomenon where you start to get these very small length vectors appears a lot. Another way to put that is that this 1 plus epsilon 1 looks very similar to this 1, 1. Right? So for the most part, his projection is already taken care of, and the remaining part is very small. So sort of this idea of Gramschmidt where you want to just keep finding the remaining part and then normalizing it maybe isn't the best way to implement QR. Does everybody agree with me? Cool. You guys are sleepy today. Maybe the homework was too hard. Okay. So, right, so there are sort of two strategies for QR factorization. We've already talked about one. Okay, so you're going to take this matrix A, and you're going to post-multiply him by a bunch of upper triangular matrices. Conveniently for once, I managed to leave this on the board. And in the end, you get a factorization QR. By the way, this matrix is easy to invert, right? Because we know how to invert these upper triangular elimination things pretty easily. In fact, this is also on your homework. So we have a way to factorize QR, but is this the only one? No. Can somebody propose, probably, given the language that's on this slide, does somebody want to take a guess at what the other algorithm is going to be for QR factorization? Don't all speak at once. No? So I do post-multiplication to get to a orthogonal thing. Alternatively, I could pre-multiply and try to get what? Now I can pre-multiply by orthogonal things and get, what is R?
Upper triangle.
An upper triangular matrix. Right? So I have two strategies. I can post-multiply by upper triangular things and get an orthogonal thing, or I can pre-multiply by orthogonal things and get an upper triangular thing. Right? By the way, why don't you think you saw a similar slide to this when we talked about LU factorization? Well, in that case, both L and U are triangular matrices, so it turns out Gaussian elimination on columns and on rows is not appreciably different. Right? But in this case, you have two different types of objects. Q and R are fundamentally different animals, and we have to treat them differently. Yeah. So let's think about this second strategy a little bit more. Right? Well, how might we implement this type of QR factorization? Well, this is actually an interesting puzzle, and when you read through your textbook, I don't think it actually motivates it very well. But to me, this second strategy, we're going to cover, by the way, there are lots of ways to do this. We're going to cover one called householder QR. There are other ones. In fact, another very common one is called Givens QR, which is sort of used for using like tweezers and extrapolating big numbers in a very numerically nice way. But householder, I think in practice, is one that shows up the most. What is householder QR going to do? Well, it's going to try and re-implement Gaussian elimination, right? That's the only way we know how to get upper triangular things so far. But rather than pre-multiplying by elimination matrices like forward substitution, it's going to try and pre-multiply by orthogonal things. So to me, this is what householder's goal was when he tried to think about this QR factorization method, is can I re-implement Gaussian elimination and get, at least the first step, this forward substitution stuff, in a way to get an upper triangular matrix, but instead of doing forward substitution, now we're going to try and rotate, right, which is effectively what these orthogonal things are doing. So let's think about some detail. So remember our pattern when we were deriving Gaussian elimination is we said, well, what are some simple things that we can do to rows of matrices? Right? We came up with, I think, 3, right? We can scale, we can permute, and we can forward and backward substitute, right? And then we wrote down Gaussian elimination, pardon me, as sort of a composition of these 3 operations. Okay? But those operations are not they're not orthonormal matrices, so they're against the rules now for QR. Right? We have a new game. And so for our new game, we need to think of some new set of operations that's going to be equally easy for us to play with. And if we're a householder, then we use reflection matrices. By the way, the given strategy uses rotation matrices. Right? These are the two sort of obvious isometries of our. Wow, that was a big word. The two sort of obvious ways to preserve lengths and angles. Right. So what is a projection matrix, or rather a reflection matrix? Okay, so here's V1, here's V2, right? So before we projected V2 onto V1. Obviously, this operation can lose information, it projects, it is certainly not preserving the length of V2, or else we wouldn't have to keep dividing by the norm during Gramschmidt. Yeah? So let's call this thing D. Right? And all we're going to do, if we reflect, is we're going to add another V. Right? So what did this do? This thinks of V as sort of a reflection plane. Right? And it's going to project V2 onto V1, and then it's going to just flip it over to the other side. Right? So just go an equal distance in the other direction. Right? And this operation, it is not orientation preserving, right? Ants moving around your Mobius strip would not like this. But for our purposes, is perfectly fine, and it preserves lengths and angles. Right? This is reflection. And so this is going to be our basic operation for doing householder QR factorization. So let's work out some mathematical details. In fact, I was nice to myself and went ahead and put the steps of the proof on the slide. So what are we going to do now? Well, we're going to take, so let's say we want to reflect B over a vector V. Hopefully that language kind of parses. What are we going to do? Well, if we subtracted 1 times the projection from B, right, that would put me here. And now I got to do it twice to get to the other side. Okay. So let's just substitute in our favorite projection formula. Yeah. And on the second line, all I've done is said, okay, what is a dot product? Well, it's a scalar. Yeah. A scalar is a 1-by-1 matrix. Yeah. So really, if we scale V by this ratio of dot products like I've done here, this is the same thing, right? So in general, right, if C, let's just do this actually. Right. So we have V dot V divided by V dot V times another V. Yeah, like that. Well, this thing is a 1-by-1 matrix. Or rather, this guy is a 1-by-1 matrix. This is an n-by-n matrix, n-by-1. And this is 1-by-1. So if you're thinking in terms of matrix algebra, can you multiply like this? No, right? Because the inner dimensions have to match up. Right? In practice, we kind of know that this number is a scalar, so this notation is okay. But in reality, what we should do is move this v to the left-hand side, and then life is good. Right? So we'll think of this as V times, and I'll remove the dot, I guess. And then this thing is going to be V transpose V divided by V transpose V. Right? And now all the dimensions work out. And now what I'm going to do is maybe we'll write the fraction like that, is I'm going to group it the other way. So what size is this matrix V transpose? N by N. Guys, see, like I'm not going to continue to answer my questions, so I might as well just say something. Okay. So now I can factor it the other way, right? I get a V on the right-hand side. And then what is this matrix here? Well, this is the matrix of the reflection over V. And we'll call him H sub V. Okay, see what I did there? This is a pattern. This is another one of these patterns that you guys should be picking up from linear algebra, right? We expand the whole expression, and then we group terms the other way, and we collapse it back together again, and out comes a nice matrix that we like, right? So in fact, that happened here. We'll call this matrix H sub V, and he's going to be what's important for moving B around. Okay. So now, if we want to proceed in analogy to forward substitution, what do we have to do? So let's say that A is the first column of our matrix capital A, right? Then what should happen is if I left multiply by this reflection matrix, I should get what? Well, I should get a multiple of the first identity vector back. right? Why is that? Well, let's think about what forward substitution is doing. Remember that we get A looks like a bunch of this kind of stuff, right? Maybe one more round just for good measure. Yeah. And what I'm saying is, after the first step of forward substitution, we want something that looks like, well, we'll just put a C there. I don't really care if it's a 1 or not. That's not a big deal. But I want zeros down the first column, right? Because this is our way of getting upper triangular stuff. You know what happens over here? Who knows? Yeah? So the question is, what if this is what we want to have happen? What does this tell us about life? Well, let's plug in our expression for the reflection matrix, right? So in the end, we'll get, or not in the end, we're going to do this calculation. CE1, right, is equal to HV, right, the reflection over V of A. By the way, what is our unknown right now? It's V, right? We're trying to figure out what V to reflect over that will have this effect on our matrix. Yeah? This is important to keep in mind, like, why the heck are we doing this? So, what is H sub V? Well, remember we had this on the previous slide. V is equal to I minus 2V transpose over V transpose V times A. Okay, this is what we derived before. And now, well, what can I do? Well, let's undo the grouping that we did before. Okay, so we'll say this thing is equal to A minus, and we'll say we're going to pull this V out times 2V transpose A divided by V transpose V. Right, so I just grouped stuff back the other way that I had it before. In fact, I guess I could have skipped the matrix step and just moved the projection. Okay. So now, what can I do with this? Well, I'm going to move this V to the left-hand side and the E to the other side, yeah? So I'll get V times 2V transpose A divided by V transpose V equals A minus CE1. Right? All I did was shuffle the terms around, and this is just a scalar, so I'll multiply by the reciprocal of this guy, and in the end I will get the formula that we know and love if we write up course notes on QR factorization, and that formula is that V is equal to, I got it here too, A minus CE1, and then just times the reciprocal of this guy, which is V transpose V, divided by 2V transpose A. Cool? So, what does this tell us about life? First of all, what do we know about the relationship between H of V and H sub 132V? Oops. What do we know about the relationship? They're equal. And why is that? Well, because all we're doing is reflecting over a direction. We're not reflecting over something that's scaled up and down. Right? And if you look back at our formula for this reflection matrix, you'll notice that every time we have a V, we divide by his norm. Right? So that sort of thing, so from that standpoint, what does this equation tell us about life? Well, the thing on the right-hand side is just some scalar. So really what this is saying is that V is parallel to this vector A minus CE1. Yeah? And in fact, the norm doesn't really matter. So just for fun, since I can scale this thing up and down any way that I want, I can say, in fact, we will define V to equal A minus CE1. See what I did there? This is a cute trick. You know? And now, what can we do? Well, remember that we still have this funny unknown C, but now we accidentally specified C by making this equality an equality. You know? So we have to go back and do our homework. Yeah? So how can we do that? Well, we know, let's move terms around again. we know that this thing is the same as CE1 equals A minus B. Okay, so if you take norms on both sides, then you know that mod C is equal to mod A minus B. Right, because the norm of this guy is 1. Yeah. And, by the way, I'm not writing the subscript 2 in this lecture, but hopefully you realize by now that I'm using the 2 norm today. That was my bad. I'm sorry. Okay, and if you go back and plug in this thing, right? Oh, wait, you can't do that. Wait, what am I missing? All right, who wants to tell me why the norm of V is, rather, the C norm, absolute value of C is equal to plus or minus the norm of A? Why is that true? You can see why this is, if I plug this back in, I'm going to get the C equals C, which was my big grand conclusion today. And of course, your instructor being lazy, skipped the last step and forgot this. Oh, right, okay. I want to waste more time on this, probably.
Well, because I think there are two axes that you can reflect the A vector so that you can get the
Oh yeah,
vector
oh sorry. Yeah, so that's why there's an absolute value here. But I'm showing why is this norm of A? No. Oh, well, it's got to work out by, if you take the dot product of, we'll worry about it later. Okay, I will get back to you on Piazza, and I'm very sorry for being a highly irresponsible instructor and forgetting the last step of this proof. But if you'll believe me for now, the absolute value of C is equal to mod A, and it's for a very stupid reason that is escaping me at the moment. That's embarrassing. But you do realize how, by making this decision, V equals this guy, I have specified C. Remember, I had two unknowns, sort of, V and C here, and then I said, well, I know that V is, all that this equation tells me so far is that V is parallel to this thing, so now I'm going to specifically choose V to be equal to this thing. And by doing that, I've accidentally specified C, which apparently is equal to A. And I'll think about that. That's kind of fun.
I think another way to compute the x maybe you can use the vector A plus the norm of A times E1 and over 2.
What was that?
And then you can add the value, add the vector and the reflected vector and compute their average to get the x.
We'll think about it at the end of class. My bad. It happens. Okay. But my little math flarp aside, what happens if we pre-multiply by h sub v? Well, by construction, we get a c at the top and zeros underneath, and we don't know what the heck happens on the rest of the matrix. No? So this is the first step of Gaussian elimination, sort of, right? Now using reflection matrices instead of these forward substitution things. And in fact, we can basically repeat the same proof, but now we're going to separate A into two vectorized things, and we want to zero out the A2. And we can go through the construction and find a similar expression for V when you do that. So what happened? So how do we do householder reflections for QR factorization? Well, all we do is we guess a V each time that's going to kill